Hi everyone, thanks for your interest in our paper. This is Jeonghyeok Do, Sungpyo Kim, Geunhyuk Youk, Jaehyup Lee, and Munchurl Kim. We are glad to present our work, PAN-Crafter, Learning Modality-Consistent Alignment for PAN-Sharpening. Remote sensing imagery is crucial for a wide range of applications, including environmental monitoring, defense intelligence, and urban planning. Many of these tasks require high-resolution images that preserve both fine spatial details and rich spectral information. However, due to inherent limitations in sensor technologies, a single imaging system cannot simultaneously achieve high spatial resolution and high spectral fidelity. To overcome this constraint, modern Earth observation satellites employ dual sensor systems, consisting of a high-resolution panchromatic (PAN) sensor and a low-resolution multispectral (LRMS) sensor. PAN-Sharpening aims to fuse high-resolution PAN images with low-resolution MS images to produce high-resolution multispectral HRMS outputs. The goal is to retain the spectral fidelity of MS images while preserving the spatial details of PAN images. However, a fundamental challenge in this process is cross-modality misalignment, which arises from differences in sensor placement, acquisition timing, and resolution disparity. Most existing pan-sharpening methods assume perfect pixel-wise alignment and rely on per-pixel reconstruction losses, such as L1 and L2, leading to spectral distortion, double edges, and blurring when misalignment is present. However, real-world pan-MS pairs often exhibit spatial misalignment, leading to spectral distortion and double-edge artifacts. To address this, several works have explored spatial adaptive feature alignment strategies. SIPSA explicitly identifies misalignment as a critical challenge in pan-sharpening and introduces a spatially adaptive module, but its fixed-scale alignment mechanism limits flexibility when handling diverse misalignment patterns. LADConv and CanConv adopt non-local spatial adaptive convolution modules that enhance feature consistency through self-similarity. However, these methods primarily focus on semantic feature aggregation rather than explicit geometric alignment, making them suboptimal for correcting cross-modality shifts. Effective pan-sharpening requires a solution that not only aligns textures and structures across modalities, but also ensures modality-consistent feature refinement at multiple spatial scales. We propose PAN-Crafter, a modality-consistent alignment framework designed to handle cross-modality misalignment during the fusion process. We propose Modality Adaptive Reconstruction (MARS), a unified reconstruction framework that enables robust learning from misaligned PAN-MS image pairs by dynamically generating both HRMS and PAN images. We introduce Cross-Modality Alignment-Aware Attention (CM3A), a novel alignment mechanism that adaptively refines textures and structures between PAN and MS images, improving spatial spectral consistency. Our goal is to learn a PAN-Crafter network that synthesizes a HRMS image from the given PAN and LRMS inputs, while explicitly handling cross-modality misalignment. We introduce Modality Adaptive Reconstruction, (MARS), a dynamic mechanism that enables the network to selectively reconstruct either HRMS or PAN images, depending on the modality selection, MARS mode. By jointly learning to reconstruct both HRMS and PAN images within a shared network, PAN-Crafter effectively incorporates sharp spatial structures while maintaining spectral fidelity in the HRMS prediction. In MS mode, the network learns to align structural details using Cross-Modality Alignment-Aware Attention (CM3A), predicting the final HRMS output. Conversely, in PAN mode, the network predicts a multi-channel version of PAN. By leveraging spatial structures and spectral fidelity of PAN and MS images, MARS ensures high-frequency details are preserved while minimizing spectral distortion. To ensure stable training, we duplicate each network inputs along the batch dimension, processing one instance in MS mode and the other in PAN mode. This enables the network to learn modality-specific features while maintaining consistency across both reconstruction tasks. For each mode, we apply the L1 loss independently to the predicted HRMS image and the back-reconstructed multi-channel PAN image, ensuring spatial and spectral fidelity. Our CM3A dynamically aligns features based on the selected Mars mode by integrating both self-attention and alignment-aware attention mechanisms. CM3A enables bidirectional alignment by transferring MS texture to PAN structure during HRMS reconstruction, and PAN structure to MS texture during PAN back reconstruction. This mechanism not only mitigates cross-modality misalignment, but also ensures structural and spectral fidelity in the reconstructed images. We compare PAN-Crafter against deep learning-based PAN-Sharpening methods on Worldview 3, Gaofen 2, and QuickBird datasets. Our PAN-Crafter consistently outperforms existing approaches across most evaluation metrics while maintaining low memory consumption and fast inference time. Notably, our method surpasses diffusion-based models in both full and reduced resolution datasets, demonstrating that our CM3A module effectively handles local misalignment without the computational burden of iterative diffusion process. Specifically, PAN-Crafter achieves 328.3 3 times and 1110.78 times faster inference time compared to PAN-Diff and TM-Diff, respectively. Additionally, compared to CanCon, which relies on k-means clustering for kernel generation, PAN-Crafter is 50.11 times faster, highlighting the efficiency of our locally adaptive alignment strategy. Comparison of PAN-Sharpening results on the Worldview 3 dataset at full resolution for very recent methods and our PAN-Crafter. Our proposed PAN-Crafter produces pan-sharpened images with minimal artifacts, especially near buildings and cars, while other approaches often yield blurred or distorted results. Visual comparison of pan-sharpening results on the Worldview 3 and QuickBird datasets at full resolution. Only our proposed PAN-Crafter is capable of generating high-quality images with clear edges around cars, buildings, and crosswalk lines, whereas previous methods tend to produce blurry and distorted results from misaligned input PAN and MS pair images. Visual comparison of pan-sharpening results on the Gaofen 2 and QuickBird datasets at reduced resolution. The blue-colored insets represent error maps computed against the ground truth, where brighter regions indicate higher reconstruction errors. To assess the generalization capability of PAN-Crafter, we conduct fully zero-shot evaluations on the Worldview 2 dataset, an unseen satellite dataset not included in the training phase. While existing methods suffer from performance degradation due to domain shifts and sensor variations, PAN-Crafter demonstrates superior generalization ability, achieving the best performance across all key metrics. Our PAN-Crafter produces sharper details with fewer distortions compared to existing methods, demonstrating superior cross-satellite robustness. The strong generalization stems from our modality-consistent alignment strategy, which explicitly mitigates cross-modality misalignment without relying on dataset-specific priors. Ablation studies on CM3A and Mars on the Worldview 3 dataset. Notably, the combination of both components achieves the best performance, highlighting their synergistic effect in jointly refining spatial and spectral consistency. Thank you for listening, and please feel free to visit our project page.